Let's see how Fresnel explain rectilinear propagation of light or approximate rectilinear propagation of light. For that, he constructed half period zones of very small area. Let us consider a plane wavefront A, B, C, D and a point on the screen, let it be P, as shown in the figure. So Fresnel draw a perpendicular from P to the wavefront O. See the figure, the center of the plane wavefront is O. So that the distance between O and P is represented as B. Okay. Now he constructed concentric spheres with the radii equal to B plus lambda by 2, B plus 2 lambda by 2, B plus 3 lambda by 2, etc. Okay. And they touch on the plane wavefront at M1, M2, M3, M4, etc. So now we are getting concentric circles on the plane wavefront ABCD with the radius OM1, OM2, OM3, OM4, etc. which can be given as R1, R2, R3, R4, etc. So the point O can be named as pole of the wavefront with respect to the point P on the screen. So, if we are considering any point on screen, you have to drop a perpendicular from that point to the wavefront. And that point will be the pole of the wavefront with respect to that particular point on the screen. Here we are considering the center of the screen, let it be P, and we are dropping a perpendicular from P to O such a way that O is the pole of the wavefront with respect to the point P. And that distance we are considering as B. In this case, we know that the waves, secondary waves emitting from O and M1 travels through a distance B and B plus lambda by 2 respectively. That means they are having a path difference equal to lambda by 2. Now if we are considering secondary wavelets from M1 and M2, again the distance is B plus lambda by 2 and B plus 2 lambda by 2. There is also a difference in path equal to lambda by 2. So Fresnel constructed this half period zone in such a way that the waves from one zone will be having a path difference equal to lambda by 2 or a phase difference equal to pi, or they are out of phase. That's why the name half period zone came for this region. Now simply we can see, you can look at the board and you can see that a 2 pi or 360 degree corresponds to a wavelength. No? Therefore pi corresponds to lambda by 2. Or in general, phase difference and path difference can be related like this. Phase difference is equal to 2 pi by lambda into path difference. So this is the peculiarity of half period zone. So this is the way how to construct half period zone. Now the point P on the screen, the effect at the point P on screen depends upon the number of half period zones exposed to the point P, as well as the distance of the point from each half period zone and inclination factor also depends upon the area of each half period zone, because as the area of half period zone increases, the number of secondary wavelets emitting from each each half period zone will be larger. So the effect at P increases with the area of half period zone, or as well as it depends upon distance and obliquity factor. So that now we are going to consider the area of the half period zone of the plane wavefront. Now let us see what is the shape of the half period zone. By constructing half period zone, we are getting concentric circle on the plane wavefront with a radius OM1, OM2, OM3, etc. See the figure. I have represent the first half period zone as 1, second as 2, and third as 3. So the first half period zone, the shape of the half period zone is a circle having radius OM1, and the second half period zone is an angular region between radius of two circles having radius OM1 and OM2, and so on. Therefore, now we can find out what is the radii of each half period zone in order to find out the area of each half period zone. For that, we are considering the second figure. We know that that's a vertical section of the wavefront. So OM1, the concentric sphere drawn with the center as P will touch at M1 as well as M1 dash, M2 as well as M2 dash, M3 as well as M3 dash, and so on. So we are getting half period zone on, if we are dividing the plane wavefront into two halves, upper half and lower half, there will be half period zone in the upper half as well as the lower half. So if we are considering the radii of half period zone, for that we are putting OM1 as R1, OM2 as R2, OM3 as R3, etc. And you know that OP is B, PM1 is equal to B plus lambda by 2, PM2 is equal to B plus 2 lambda by 2, etc. Now consider the right angle triangle M1OP. So according to Pythagoras theorem, OM1 square is equal to M1P square minus OP square. Substituting the value of M1P and OP, we are getting B plus lambda by 2 the whole square minus B square. We are expanding B plus lambda by 2 the whole square as A plus B the whole square. So we are getting B square plus B lambda plus lambda square by 4. So minus B square and plus B square cancel each other, and we are getting B plus B lambda plus lambda square by 4. And you know that the wavelength of the monochromatic light is of the order of nanometer, and distance is very large comparing with that. Therefore, we can neglect the second term. So the radii OM1 is given as R1 is equal to root of B lambda. Now we can consider the radii of the second half period zone. For that, we are considering the right angle M2OP. So OM2 square is equal to M2P square minus OP square. Substituting for M2P and OP, B plus 2 lambda by 2 the whole square minus B square, and expanding that, B square plus lambda square plus 2B lambda minus B square. Here also B square and minus B square cancel each other, and also lambda square is very small comparing with the 2B. Therefore, OM2 square can be approximately taken as 2B lambda. So OM2, which is represented as R2, can be taken as root of 2B lambda. So in general, the radii of the nth half period zone, the circle of the outer circle of the nth half period zone can be taken as Rn is equal to root of nb lambda. So in general, the radii of half period zone is directly proportional to the square root of natural number as well as the distance of the screen from the half period zone B and the wavelength of the light we are using.